So today we will apply the formalism of Golan categories. We'll consider the main example. We will consider the category of finite étale covers. And using that formalism, we define the étale fundamental group. OK, so let's say section 1. So I want to recall for you what an étale morphism is. This central role in this. So, so definition, proposition, amorphism of schemes. Let me f from x to y is étale. If equivalent conditions so first condition, so first definition of étale morphism is, well, probably the most geometric one is the following. Lifting property. So of finite presentation. So locally finite presentation. So I should have started this lecture by recalling for you what this condition means. This is not the end of the definition. So that's a very technical condition. That's why I don't want to distract your attention to this, but I will recall it here, what this locally of presentation is. So definition, OK, so f from x to y is locally of, OK, maybe two. So suppose first that this is affine schemes. OK, is locally of finite presentation if this map from B to A factors as follows. So it's so this is A of polynomial algebra, so finitely many variables, modulo a finitely generated ideal. Okay, so this is an isomorphism. This is my f. So yeah, I think it's okay. So this condition is stronger than saying that B is of finite type over A. So B of finite type over A means that B is finitely generated A algebra. And here I require also that it has finitely many relations. So if A were Noetherian, then of course this is equivalent to saying that it's just of finite type. And B any in general, so if I have any morphism is locally of finite presentation if for any affine open so x goes to y, and here you have open subset spec A, and here spec B, such that this subset goes to this, f restricted to A is locally of finite presentation. Okay, that's the definition. Yes, so and the property is that fact that finite presentation property is Zariski local. That's stated similar to the property of finite type morphisms. So what it means is that if you want to check that a morphism from x to y is locally finite presentation, it suffices to check that for every point of this scheme there exists a neighborhood, a affine neighborhood of this point, and an affine neighborhood of its image, such that this induced morphism is of finite presentation in this sense. Okay, so again, this is very technical, and the key. Ну, например, для этого, давай, Катя, раз спросила, what we are going to use today. Well, why this condition is better than, so this is stronger than saying that f is of finite type. And why do we need this? So here is a fact that I'm going to use many times. So if f is a flat locally a morphism of flat locally of finite presentation morphism, then f is open. So you're right that we also need this, we'll use this condition when we will discuss descent, but this is another result where this condition is used. So I will so open means that, of course, image of an open set is open, so f of x is open in Y in particular. So here is an example where let's consider the following example. Let's take a morphism k of t. This is the field of rational functions, and let's map it to spec k of t. So this is just a fine line. Is this morphism flat? Sure, because this is a field, and as a module over this guy, it's flat. It has no torsion. That's enough. So is flat, but not. Is it open? Is the generic point in the affine line is open? No. closed subsets of a finite line are just finite collection of closed points, and well, that's not the complement to this. So is not, but not open. So this looks like a contradiction, but of course this is not of locally finite presentation. So, well, you need some condition for this to hold, and so if in the case when x and y are Noetherian, so then this is, as I said, equivalent to this morphism be locally well finite type, then this fact admits a relatively simple proof using Chevalier Theorem. So you need to, Chevalier Theorem asserts that image of x is constructible in y, and then the property of being open for constructible sets is equivalent to saying that this image is stable under generalization of points. So if one point lies in the closure of another, then so if sort of closed point is in the image, then the generic point is also in the image. So and this condition follows easily from lattice. Okay, so this holds in general, as I said. That's what we're going to use. So local presentation and has what's called the infinitesimal lifting property. So what is it? It's the following. So suppose you have diagram x goes to y. This is my f. And you have some affine. And you have a closed subscheme. Zero thickening. So what it means is that if this is spec A, spec A mod I for some ideal I whose square is 0. Okay? Now, suppose you have a commutative. Then the infinitesimal lifting property asserts that there exists a unique map that makes everything commutative.
Why both of the right-hand side schemes are denoted T?
Good question. So this is T0. Okay? So, okay, so this is the first definition of amorphism. And maybe let me give an example here. So kind of explain what it means. So in particular, it means that so we can take x, y, we can take just for t spectrum of the dual numbers, and here I have spec k, so whenever I have a diagram like this, the assertion is that there exists a unique map, which means that F is isomorphism on Zariski tangent spaces. Very good. So, and of course, once you have this, you can formulate a stronger condition by induction. You can replace this condition by just saying that I is nilpotent. I to some power n is 0. Now, yes? Фробениус совершенно нейтральный. У него дифференциал в каждой точке равен нулю. И он в касательных пространствах индуцирует нулевое отображение. Good. So this is kind of geometric definition. Now the following is so that's what you use in kind of geometric proofs. If you want to check that something is étal, one usually uses the following. So f is, so that's equivalent, is again locally finite presentation, flat, and also the relative differential forms is 0. Okay? So third condition, let's see, I want to say here, three. So again, flat, f is a locally finite presentation, flat, and for every point, y in y, its fiber. Let's see. So I want to call it x, y, and this is fiber product. So I have the residue field of my point k of y. It maps to y, and this is the fiber. So the fiber x, y is a spectrum of some algebra where this algebra is, so this is an algebra over this residue field. And the condition is that it's a direct product, how do I call it? Product, possibly infinite, of some fields with each ki contains my residue field, finite separable extension. So fibers are in particular reduced. There is no nilpotence, and they remain reduced after any base change. Now, if you combine this second definition with this fact, you see that an automorphism is always open. Okay, and then there is another definition, which is Jacobian criterion of etalness. Also useful for. Let's see. for every point x in x, you have, there exists, well, an open neighborhood and also open neighborhood of y, which is f of x in x. So you have x, y, you have here this u, and here you have w. Well, there exists such affine neighborhoods. So this is spec A, and this is spec B. So A has the following form. A is the quotient of polynomial algebra in n variables modulo ideal generated by the same number of equations and with the Jacobian matrix df I over dxj determinant this determinant of this matrix invertible in A. Okay. Good. So I will not give a proof of this. So I will of the equivalence. I will Telegram channel. I will give a good reference for all this. But though I will not give a proof, let me give an example showing how this works. So let's yeah.
Sort of definitions. First, if we take X to be an infinite disjoint union of Y's,
yes,
F to be a projection, then 1, 2, and 4 holds, and 3 doesn't hold.
3. Why it doesn't hold?
Because the fiber of any point is a disjoint union of infinite number of points, which is not quasi-compact, hence not affine, hence not a product of spectral products. It is. It's locally an open immersion. It's locally isomorphic. It's locally everything. An infinite disjoint union of specs surjects onto specs perfectly. But the infinite union of specs is not affine. It's not spectral.
It shouldn't be local on the base, but not on the target.
So let's think. So you are saying that if I find a presentation, значит, вы предлагаете просто взять дизъюнтное объединение счетного числа копий точки, спектра C, и спроектировать это все на точку. Значит, это не то же, значит, flat, да. lifting property. Locally presentation. Is it so let's see. So I definitely don't want this morphism to be a tull. I don't like it. So f is flat. Flatness is local. Okay, so let me send you. Okay, very good question. Thank you.
First one, and so sort of extending the discussion we had last time.
Yes.
If you said f is a finite presentation, then that would make the étal site small. But if you say local or finite presentation, then the étal site is not small, and we can't do what we're trying to do. So what is the role of this sort of distinction that you make it? So that we allow this infinite disjoint unions and possibly making the site not small.
Maybe so. You are saying that good. So you are saying that I can correct it, probably, right? So probably the correction is that that I should do is that so I should write that this is disjoint union of spec ki, right? Then probably it will remove your objection. Не афинный, но вот такой.
Нет, тогда получается, что этот пример
удовлетворяет всем четырем. Да, получается, что удовлетворяет. Значит, давайте я, вот скорее всего, скорректировать нужно вот так, но я, значит, проверю это и вам напишу. Окей?
Насколько нам важно вот, разрешать такие примеры, а то у нас сайт большой получается. Мы можем ограничиться?
Ну, терминология как бы общепринятая, я не хочу ее менять. Хорошо? В определении тального аморфизма оно... Вот. Да, нам не очень нужно, конечно, это, но тем не менее. Okay, so let's. I will check that whether this is the right way of saying it. Thank you. Now, so let's prove a lemma. Just to play with this definition a little bit. So let's prove that. So if you have a diagram x prime y, this will be f, this will be g, and any map h with f and g are tull, then this implies that h is a tull.
You were also about to give a reference for
Yeah, so I will. The reference will be a commutative algebra book by Akil Matthew, but I will send the telegram. Okay, so I will just restrict myself to checking the infinitesimal lifting property for H. I will not check that it's locally of finite presentation. So proof, check infinitesimal lifting property for H. Okay, so here is what we have. We have x, we have x prime, we have h, we have some t0, and we have t affine. So this is infinitesimal thickening. So we have a commutative diagram, and so this maps to y, and we want to show the existence of this uniqueness of this arrow that makes everything commutative. Okay, so let's give some name to all this. So let's call this I. Oh no, sorry. This is P. This is Q. This is G. Yeah, I think that's enough. So so we know that that the composition of étale morphisms is étale. So this morphism is so H composed with G is étale.
Мы еще не знаем, что...
Композиция, то, что композиция этальна.
Нет, это мы знаем по условию.
Да,
Знаем, что H этальный.
да, правильно. Значит, мы знаем, что F этальна. Очень хорошо. Значит, okay, so we have, let's consider this diagram, and let's apply the étalness, the infinitesimal lifting property for this morphism to this diagram. So there exists, it follows that there exists a unique map Q tilde such that if I, well, what are the properties? So two properties. If I compose G with H and with Q tilde, right? So then this is the same as G composed with Q. Мы сначала идем сюда, а потом сюда. И это то же самое, что пройти вот так. This is the first property. And also I know that take Q tilde and restrict it to T0, I get P. Okay, so let's see what we want to show. What we want to prove. We want to prove that so if I go this way, if I just take H composed with Q tilde, I get Q. So in other words, I want to show that you can cancel by G here, right? Okay, so how to check this? Okay, so we have, so what is it? So we have, let's consider now the following diagram. So we have two morphisms here. One is this H composed is Q tilde. And so what do we know about these morphisms? We know that they agree. So this is what we know, that they agree H composed with Q tilde is restricted to T0 is equal to Q restricted to T0. That follows from this property. Okay, and we also know that we also know this. So now let's maybe erase this. Let's forget about this part of the diagram. So so just remember this diagram. So you see, we can consider, so let's apply the uniqueness statement here. So So this morphism, G is étal. So since G is étal, we have that H composed with Q tilde is equal to Q, right? So I know that whenever, so this is an étal morphism, I have a morphism from T0, and this is infinitesimal thickening, and there is only one way to extend it to a morphism from T, right? Okay? This proves the infinitesimal lifting property. Good. So corollary is that if x to y is étal, then the diagonal, which is a map from x to x times x over y, this is the diagonal, is open. Okay? So why is it a corollary? So proof, well, so consider the diagram, x times x over y, and this is y. This is projection, projection, say first projection, then this is a commutative diagram, so which implies that by the length that we just proved that delta x is étal. And therefore, it's open. So, for separable morphisms, the diagonal is also closed, right? In all examples we care about, the diagonal is also closed, so it means that it's a connected component. Well, it's a union of connected components. This is a very nice geometric property of étal morphisms. So notice that we do not require F to be separable in general. Separated. So for example, if you consider a fine line with double point, the standard example of a not separated scheme, then its projection to the affine line is an étal morphism because it's locally an isomorphism for the risky topology. Okay. So now let's move further. So we have we want to define the appropriate Galois category, and the category that we need is finite étal morphisms. Finite étal morphisms. So we define a category, finite étal over x. This is going to be a category whose objects finite, whatever this is, finite étal to x, morphisms well, so if you have two such guys, then this is just commutative diagram. Okay? So finite means that just this map F is finite. Okay. So here is a lemma, a characterization of finite morphisms. So let F from y to x be, say, finite flat morphism. So, so the following two conditions are equivalent. Weil. Second condition is the following. So before I formulate it, so let's observe that so this condition that F is finite and flat implies that the direct image of the structure sheaf on Y, well, first of all, it's a coherent sheaf on X. It's finitely generated, but in fact, it is a vector bundle. Over X, right? So why that? Because by definition of flatness, this is a, well, finitely generated OX module, and it's also flat. And every finitely generated module which is flat is locally free. So now I can calculate the condition. So for every point x in X, say spec A
So if you're worried about non-serious settings, does finite imply finite presentation so that is a model finitely generated or finitely presented, and do we need this?
I don't think that. I think finitely generated module, which is flat, is locally free.
So finite flat does not entail
Yeah.
finite presentation, and this is
Yeah.
necessary.
Yes. So okay. So such that for any such that global functions be these are functions on I will write it here. So I take open subset and I take this preimage, which must be affine, because my morphism is finite. So particularly, it means that preimage of affine is affine. And so I will write it here. So such that for B is free A module. Okay, so the trace form Q from B times B to A, so Q of B1, B2 is equal to the trace of B over A, B1, B2 is non-degenerate. Okay? So what does it mean? So, okay, first I read what is written here. So this is one condition, and the other condition is that for every sufficiently small neighborhood of every point x, sufficiently small means that this B is free A module, right? So I know that it's, in general, it's locally free, but, well, if I shrink my condition, it will be free. Then, so I can look at this trace form. So what is trace of B over A? So B1 times B2 is an element of B, and I can think of B, well, B is a free module of finite rank over A, so I can consider multiplication by this element. It defines me an endomorphism of this free module, and I can take its trace, right?
There should be OY of F minus 1, because F minus 1 of A is the subset of Y.
Yes, thank you. Thank you, thank you. Mm-hmm. Okay, so what does it mean that the form is non-degenerate? It means that its gram matrix has invertible determinant. It's stronger than saying that for every B1 there exists B2 such that this is non-zero. Mm-hmm. So why is that? So let's, I don't think that this proof, this lemma requires too much argument. So what we need to check is that the fibers are disjoint union of separable extension of fields, spectrum of separable extension of fields. So proof reduces to Y equal to spec K. Because once we know that my morphism is flat and finite, so it's in particular, sorry, maybe I should add here. Let's see, finite, be finite flat, locally finite presentation. So once I know that I have this condition, so the tallness is sufficient to check on fibers. So what happens on fibers? Well, this form restricts to a form on the fiber, so, and this immediately reduces the proof to this case. Mm-hmm. Because, so I want to show that the determinant of this gram matrix is invertible, and it suffices to show that it's non-zero for every point of spec A, right? If you have an element of spec A, which is,
because A may have no potence.
and so what? If it's non-zero, it doesn't matter. So if you have an element of A, which is invertible when you mod it out by nilpotence.
Even if A is non-necessary?
Yeah. Well, if you have two elements, F1 and F2, and the difference is nilpotent, if F1 is invertible, then F2 is also invertible, right?
Okay, yes.
Yeah. Mm-hmm. Good. So, so used to this case, and then what we have to check is that the trace form on this form Q is non-degenerate if and only if K is separable. Which is a well-known fact from field theory. Good. So now we have the category of finite morphisms, and I also want to endow it with a fiber factor. So definition, geometric point of X is just a morphism from spectrum of unalgebraic and from spectrum of algebraically closed field to X. So K is equal to K bar. So the image is not required to be closed. So it could be closed, closed point, but you can take, for example, field of rational functions on X if X is integral, and take its algebraic closure. So all geometric points can be of different type. So okay, so now for every geometric point, define the fiber factor fx from the category of finite étale covers of X to finite sets. So what we do, we take just the fiber fx applied to y is we take a fiber of y over this point, right, and take its k points. And I will draw the diagram here. So this is y, this is x. So this is spec k. I have here. This is my yx bar. So we are looking at points, namely sections of this map. This is the same as sections, the lifts of this morphism to y. So points of this finite set are in one-to-one correspondence with this. Why this set is finite? Because this is a finite étale morphism over a spectrum of points. So this is the joint union of finite copies of k, right? This is at the end just finite copies of spec k. Algebraically closed. Every finite étale morphism over spectrum of algebraically closed field is splits into several copies of spec k. Is it clear? Катя? Ну, это да. Нет, это просто по определению. Ну, потому что задать... Эта диаграмма, ну, во-первых, я хотел нарисовать, что такое слой. Это вот такое произведение. И кроме того, я хотел сказать, что, значит, то, что здесь написано, это просто такие сечения. И вообще, значит, ну, просто это, значит, что мы делаем? Мы берем конечное этальное накрытие индексом, берем его обратный образ на спектр алгебраически замкнутого поля, и там оно расщепляется, это накрытие. Оно просто дизъюнтное объединение точек. И вот мы берем эти точки. Вот что мы делаем. Берем слой-то. Угу. Да, да, каточки слоя. Okay. Good. So now theorem. Let me see whether I have enough. Yeah. Now I can formulate the theorem. So we have category of finite et al. Covers over X, and we have this fiber functor. Well, we have this functor to finite sets, and the theorem is that it is well, if, sorry, I have to write it better. If X is connected, this is a very important assertion, then finite tal covers of X with this fiber functor is a Gola category. So I'm going to prove this, but before I give a proof, let me make a definition. So pi 1 of X with base point X bar is, by definition, automorphism of this fiber functor. So this is a topological group, actually a profinite group, and so corollary from this theorem and the theorem that we discussed last time is that this category, this group completely describes the category of finite Gola covers, is equivalent to finite pi 1 sets. So, and what is again finite pi 1 set? It's a set with a continuous action of this. So stabilizer of every point is open, finite, of course. Good. So let's give a proof. So what we have to show? Well, first of all, we have to show that this category has limits, finite limits, and colimits. So limits. So it's enough to show that it's fiber products and final object in finite et al. Covers. So final object. What is final object? What is a Gola cover that admits a unique map to from any Gola from any finite cover? Yes. Fiber products. Well, you have Y, Y1, Y3, Y2, and you have diagram like this. So what we have, that this composition is etal, this is etal, then I claim that Y1 times Y2, Y3 over Y1 is finite et al. Over X. Why is it finite et al? just because y1 times y2. So, well, so this morphism is étal, this morphism is étal, therefore this morphism is also étal, and this is the base change, so that means that this morphism is étal, and now it means that the composition is étal. Right? So we use the first lemma that I proved. So that this morphism is étal. Что? Абсолютно. Над y2. Да, Спасибо большое. Я не понял. Да. Спасибо. Спасибо. Good. So these are fiber products. Now, so co-products. So co-products. Well, first of all, we have initial object, and this is empty scheme. That's also allowed. And we have co-products, co-limits. And first we have co-products. Well, if you have two finite étal covers, you can just take the disjoint union. This is also finite étal. So now I have to show that there exists arbitrary co-limits, and it's enough to show that there are co-products and also co-equalizers. Okay? So what I need to check is so suppose I have y1 and two maps, A and B, and I need to show that co-equalizers exist. Okay. So let's give some names. So this will be F1, and this will be F2. These are finite étal morphisms. So if I consider Fi star of the structure sheaf, this is a vector bundle on X, but it has an algebra structure, right? Because I can multiply functions. So this is a vector bundle. It's a locally free sheaf of algebras on X. So when you have a locally free sheaf of algebras, you can, in fact, any sheaf, quasi-coherent even sheaf of algebras, there is a construction of the relative spectrum. If X were affine, you would just take the usual spectrum. This would be an algebra. If X is not affine, well, then there is a kind of constructive construction. You cover X by affine, you take the usual spectrum over affine pieces, and then you glue them. But it also has a universal property. What is a What are morphisms from a schema? So it also has a universal property. So this is a scheme over X, such that for any scheme, say T over X, morphism from T guy is the same as morphisms from this sheaf to the direct image of functions on T and X. Okay. So, and this is, as you may guess, this is just Yi. So the finite morphisms over X are in one-to-one correspondence with just sheaf of algebras, coherent sheaves on algebras on X. Что? Пожалуйста. Так. So you have a sheaf of algebras, X, a sheaf of algebras, spec X, spec A, that's the notation, is a scheme such that for every T over X, and this is pi, morphisms from T to this spec A is the same as morphisms in the category of sheaf of algebras from A to pi rho star of OT. This general, so that's kind of this universal property helps to do gluing, actually. You don't have to think more. You just check that it's representable locally, and then on the, so then you pick a cover, and then on the intersections, you have automatically all the gluing conditions.
That quality holds for any affine morphisms, yes?
For every, yeah, by affine. Oh, no, it's no, any.
There for affine.
Here?
Yeah.
But this is finite et al.
Yeah. But like it was.
No, so this holds for finite morphisms, for affine morphisms. Yes. Good. So now, so take, define A to be equalizer of the following two maps of algebras. So you have F2 star of O Y2, and you have two maps, A star, B star, to F1 star OX, Y1. Right? So, well, this way you get a sheaf of algebras. So what is equalizer? It's just a space set of elements here whose images are the same. This is subalgebra here. So claim spec, this relative spec of A, is co-equalizer of A and B in finite et al. And so proof is a very good exercise, and well, what you actually need, what requires the proof here is that this spec of A is finite et al. Actually, you need to show the important thing that it's et al. That's non-obvious. And you check it using infinitesimal lifting property. Okay? And it's very similar to the first lemma that we proved today.
So what is, again, so since you're not assuming any hypothesis, what is finite? If finite is such that generated A module.
Yes.
So you define A as a kernel of some map.
Yes.
Why in the world is it finally generated?
Okay, so here is maybe one argument that would convince you, though it's right. So the property of being finite étale is stable under an étale base change. And after an étale base change, your finite étale cover splits into this disjoint union. And then it should be obvious. Étale is étale local. And so if x1 over x is disjoint union of copies of x, then it's obvious. Okay. So now we come to the connected components. Connected. So what else do we have to check? So we have limits, co-limits. We have to check that every object is sum of connected components. Connected components. So so X is connected. So if you have any Y, then you can write Y as disjoint union of its connected components. And then Yi is connected in the categorical sense. Why is it can be eaten as a union of connected?
I don't want to just assume that everything is serious because.
No, so I agree that it requires an argument, but it's this generality. So all you need is final presentation property. So if X is a Noetherian, then we know that every Noetherian scheme is union of finitely many connected components, but it's still true. So okay. And I claim that Yi, if Yi is connected, then this is a connected object in the categorical sense. And I recall what it means. It means that if I have any morphism from Yi to some Y Y prime, and this is connected. This is connected, then implies that this I is isomorphism. Okay? That's what we need to check. So what I have to check is that every finite étale cover is disjoint union, is a finite coproduct of things which have this categorical property. We say that in a Galois category, we say that an object is connected if it has this property. So how do we check that? So suppose Yi is a connected scheme. This is étale morphism, this is étale morphism, and this is an embedding. How to check that it's an isomorphism? Yeah, so by the first lemma that we proved today, it's étale, so the image is open. But these are also proper morphisms, right? Because they are finite. So the image must be also closed. So the image is both open and closed, so it's a connected component. Right? Good. So now the last property that I need to check, which is the most important one, is that my fiber functor reflects isomorphisms. So X reflects isomorphisms. So what I need to check is that if I have, again, y1 and they are finite total over x. Here I have some map, which is G. Okay, maybe, let's see. Yeah, this is G. So if, so that's what we want. So if G induces a bijection between fiber x and G is isomorphism. So we want to check that if one fiber over one point are the same, right? We have a morphism that induces an isomorphism in one fiber, then it's actually an isomorphism. So it's clear that this would fail dramatically if x is not connected because this condition tells you nothing about what happens in other connected components over the other connected components. So proof. So let's take so first of all, we may assume that y2 is connected. Why we assume this? Because if it's not connected, we write it as disjoint union of connected components, take pre-images, and so if we can show it for every that every pre-image maps isomorphically to connected component of y2, then we are done. Okay, then we take a direct image of the structure sheaf, OI11. This is a vector bundle, of some rank D. So D is the degree of this map. That's called, this is the definition of the degree, if you wish. So we want to show that D is 1. So since Y2 is connected, D is constant. And now, looking, because this formation of this vector bundle commutes with base change, so looking at x, y1, x bar, and y2 x bar, we see that D is actually 1, right? Because if I restrict my cover to point x bar, then this G is an isomorphism. So, which implies that G is an isomorphism. Okay. And this completes the proof. So here I'm using the fact that if I have a morphism of algebra such that, so this is an algebra over functions on y2, and I know that it's free of rank 1. Then it's actually isomorphic to functions on y2, which is immediate. Okay? So this is the proof of the theorem. Да. Ну просто векторное рассвоение на связанном многообразии, на него ранг-то постоянный. И это ключевое место.
В общем случае неверно, что любой конечно порожденный плоский модуль проективный.
Неверно. То нужно нотировать тоже.
Ну, или какие-то условия дополнительные. Конечно, верно.
Про конечно представленный верно.
Представленный плоский всегда проективный. И наоборот, конечно, порожденный проективный является плоским, конечно, представленным.
Хорошо, сейчас у нас конечно представленность имеется же ведь? Значит, у нас
Если B конечно порождена как А-модуль и конечно представлена как А-алгебра, то B конечно представлена как А-модуль.
сейчас. Давайте я тоже про это подумаю, но, значит, я во многих местах здесь как бы мазал, и, конечно, даже вот, в первую очередь еще со связанными компонентами, но если действительно предполагать, что база Нётерова, что будет во всех примерах, то тогда, значит, доказательство, мне кажется, полное.
Можно спросить?
Да, да.
А вот мы берем прямой образ вот о y1, да?
Да.
И говорим, что это расслоение, а еще мы говорим, что у нас тривиально. Да?
Почему тривиально? Локально тривиально. У нее только ранг постоянный. Ну в конце концов мы...
Это свободный модуль.
Локально свободный.
А почему он свободный?
Нет, ну, значит, смотрите. Вот мне не нужно знать, что он свободный. Как только я знаю, что это... Значит, вот у меня есть такая ситуация. У меня есть OY2 и есть прямой образ вот это OY1. Значит, что у меня есть? Вот это вот рассвоение со структурой алгебры. Значит, алгебры над этим делом. У меня есть морфизм алгебры. Значит, я знаю, что про это. Что, значит, вот у меня есть такой морфизм, а еще я знаю, что вот это является свободным модулем ранга 1 над этим. Но априори, конечно, образующее этого свободного модуля единица. Георгий, вы про это спрашиваете? Нет, простите, локально свободный ранга 1. Локально свободный ранга 1. Да, правильно. Значит, и вот я утверждаю, что, значит, я знаю про... Вот у меня есть вот это рассвоение ранга 1 со структурой алгебры. Вот, значит, вот есть такое отображение, которое... Я знаю, что... Значит, я утверждаю, что в таком случае, ну вот как бы образующее, что это рассвоение тривиальное, это изоморфизм просто. Но почему? Значит, здесь надо... Конечно, неверно, что если у вас есть линейное рассвоение, и у него есть сечение, то отсюда не следует, что оно тривиально. Вы совершенно правы. И это не утверждается. Но из-за того, что здесь есть структура алгебры, это следует. Давайте это хорошее замечание. Значит, я хочу доказать, что вот это изоморфизм. Так? Значит, вот это линейное рассвоение, и вот у него сечение. А еще здесь есть структура алгебры. Ну, утверждение локальное, что это изоморфизм. Я могу считать, что это тривиальное рассвоение. Так? Значит, ну хорошо, давайте я возьму какую-то его образующую. Образующую возьму. Ну, там, Т. Вот отсюда. Значит, что я знаю? Я знаю, что существует такая функция здесь, что f умножить на t равно единице. Ну, отсюда значит, что f обратимый элемент. Вот. Хорошо. А я хочу доказать, что в качестве образующей можно было бы взять просто единицу. Вот это мое сечение, собственно. Давайте сделаем это так. Значит, значит, то есть я хочу доказать, что t на самом деле лежит вот здесь. А давайте рассмотрим такую вещь. Давайте рассмотрим t в квадрате. T в квадрате, значит, сейчас, это будет, это я тоже могу получить как некоторое g умножить на t. Теперь давайте это умножим на, сейчас правильно я все делаю, да, теперь давайте я вот это равенство, значит, вот это тоже лежит в y2. Теперь давайте я это равенство умножу на f. Умножу на f, и я получу, что t равняется g. Значит, я умножаю его на f и получаю, что t равняется g. Все.
Вы не могли бы сказать, что t равно единице? Если это скажет, просто t нет нулей. Регулярное сечение без нулей. Или мы не знаем, что вот эта единица, что как вот эта единица в этой алгебре?
Нет, это, безусловно, морфизм алгебр с единицей.
Сейчас вот, окей, когда просто вот единичное сечение вот в той.
Да, порождающий. Нет нулей.
Нет нулей, да.
Нет нулей, и что?
Значит,
И что? И почему оно приходит отсюда?
вот единица в этой алгебре.
Нет, единица приходит, в этой алгебре одинаковая единица. Это морфизм алгебр с единицей. Значит, еще раз, линейно тривиальный. Значит, вот это у меня алгебра, это свободный модуль ранга 1, это гомоморфизм алгебр. Я хочу доказать, что это изоморфизм.
Но если у сечения нет нулей, то расстояние тривиально. А с другой стороны, мы знаем, что на каком-то из слоев есть изоморфизм.
Нет.
Это разве...
Нет, ну хорошо. В общем, в любом случае, рассуждение, как вы видите, одна строчка. Но тем не менее, как бы то, что здесь используется, то, что это есть структура алгебры, иначе это неверно.
просто в линейном расслоении существование одного какого-то регулярного сечения,
Да.
у которого нет нулей. Недостаточно ли из этого исключить, что...
А что... Хорошо, нет. Но отсюда следует, что это рассвоение тривиально, конечно. И что? Мы и так знаем, что оно тривиально.
Тогда окей, значит, у нас существует тривиальное расслоение.
Да.
Будет какой-то...
Но не обязательно изоморфизм.
Ну да, безусловно, да.
Но если это гомоморфизм алгебр, то изоморфизм.
Ну да, просто единица.
Да. Ладно. Нет, ну, в общем, я думаю, что то, что вы говорите, это тоже доказательство. Хорошо? Еще вопросы? А что она утверждает?
Ну, про связанные компоненты. Вот где у нас 41 до 17,3.
Ну там типа что x, ну тебе нужно представить, что это x, можно представить как линия y.
что любая схема, которая локально конечно представленная,
Если f из x в s конечный тайный морфизм схем, s точка на s существует тайная окрестность у этой точки, и разложение x u не связано объединение выжитых, так что выжитые u это изоморфизм.
Это вот то, что вы... Это утверждение, которое я предлагал использовать, чтобы значит, коэквалайзеры построить. Но это гораздо более сложное, чем тут что-то...
Но и оно же нужно, чтобы понять, что связанные компоненты существуют.
Ага. То есть, что их конечное число просто. Сейчас, и вообще, наверное, что связанные компоненты в схеме — это не очень корректно, что они вообще...
Нет, связанные компоненты, они есть в любом логическом пространстве.
Есть?
Просто
Какую структуру схем?
открыто замкнутый.
А правда, что любое пространство есть объединение связанных компонентов?
Логически нет. То есть канторово множество, его связанные компоненты — это точка.
Ага.
То есть нам не просто можно рассмотреть логическую связанную компоненту, нам нужно увидеть структуру схем. И доказать, что...
Да.
Добрый, короче, это единственное слово, если еще видно.
Вроде да, но это исправляется limit 41, 17, 3. Ну, в общем, здесь все написано. То же самое, только
Понятно,
с номерами.
Нет, все, конечно, где-то написано. Это, в общем-то, не оправдание. Я прошу прощения. Okay, so let's... Спасибо. Да.
А то, что это с звездочкой, наш слой сохраняет пределы.
Ну, это по определению, да, это потому что это, например,
Сохраняет пределы совсем очевидно.
то, что сохраняет ко-пределы тоже.
Ко-пределы.
Ну, потому что он плоский.
Коэквалайзер строит очень.
Что? Ну, коэквалайзер — это ядро отображения между некоторыми двумя алгебрами. А со звездочкой минус b со звездочкой. Но мои алгебры, они плоские над базой. Поэтому это ядро, оно коммутирует с заменой базы, то есть с переходом слоя.
Тут используется теория спуска в следующем утверждении, чтобы доказать, что плоский мономорфизм локально конечно представленный — это открытое вложение.
В общем, я видел, на самом деле, вот такое доказательство, да, по тому учебнику, по которому я готовился. Там, значит, предлагалось использовать теорию спуска, которую мы даже еще и не обсуждали. С другой стороны, я подумал, что в неотеровом случае конечность очевидна этого самого коэквалайзера. А тот факт, что это плоский тальный морфизм, можно в одну строчку проверить из инфинизимального критерия. Ну и как бы рассуждение действительно с этим самым тальным спуском, оно более общее, но, с другой стороны, оно гораздо более сложное и позволяет только в случае неотеровой схемы. Как бы,
Что еще раз там доказывается?
ну там вот...
Разложение тальный морфизм суммы связанных компонентов.
Да. Ну вот там было некоторое утверждение про то, что коэквалайзеры есть. Значит, предлагается там такое рассуждение, что локально в этальной топологии каждый конечный этальный морфизм разваливается просто в дизъюнтное объединение копий икса. Ну а потом надо доказать, что, значит, что утверждение, что свойство быть конечным этальным, оно локально в этальной топологии. Вот здесь используется этот самый этальный спуск. Вот. Но это все как бы очень сложно, заумно. Еще раз, вот в неотеровом случае можно просто воспользоваться инфинизимальным критерием.